The sun has been a basic area of strength for us, especially of late, and it will go through a principle other than enrapturing change, the inversion of its alluring field. This affiliation occurs generally at normal intervals, meaning the midpoint of the sunspot cycle. Likewise, it has wide repercussions for us here on Earth. As a matter of fact, rapidly, the sun could make it possible to present a serious gamble that could cause complete aggravation and disaster for everyone in the world. As you will see, the sun's alluring field is created by the progression of electrically charged gases in its interior, a process known as the solar dynamo. Over time, this alluring field becomes dynamically tangled and reshaped, considering the sun's rotation and convective changes. Eventually, this process leads to a complete inversion of the appealing poles. The north appealing pole changes into the south appealing pole, and vice versa. Let's break down the entire cycle and explore the sun in detail. The sun is primarily composed of hydrogen and helium as plasma, a state of matter where electrons are not bound to atoms, resulting in a mix of free electrons and ions. The sun's interior is divided into several layers, with the core at the center, encased by the radiative zone and the convective zone. The core is the sun's most critical region, where nuclear fusion occurs, converting hydrogen into helium and generating enormous amounts of energy. Surrounding the core is the radiative zone, where energy is transferred outward through radiation. Here, energy moves slowly outward as photons are absorbed and re-emitted by the solar plasma. The outer layer of the sun's interior is the convective zone, where energy is transferred by convection. Hot plasma rises toward the surface, cools, and sinks again, creating convection currents. The solar dynamo process works predominantly in the convective zone and the tachocline, a thin layer between the radiative zone and the convective zone. The tachocline is significant because it is where the sun's differential rotation and shear flows play a crucial role in generating the alluring field. Here's something fascinating you may not know. The sun does not rotate as a solid body. Instead, different parts of the sun rotate at different rates, with the equator rotating faster than the poles, a phenomenon known as differential rotation. This differential rotation stretches and bends the alluring field lines, prolonging the attractive field. The solar cycle is approximately 11 years long, during which the sun's alluring field undergoes a series of changes, culminating in the inversion of its poles. This cycle, driven by the solar dynamo, includes several stages. At the start of the solar cycle, the sun is in a state known as solar minimum, characterized by a low number of sunspots and minimal solar activity. The alluring field is generally simple and bipolar, with a clear north and south magnetic pole. As the cycle progresses, the number of sunspots increases. Sunspots are regions of intense magnetic activity and are associated with the rise of magnetic activity from the sun's interior. These sunspots appear in pairs with opposite magnetic polarities and migrate toward the equator over time. Around the midpoint of the solar cycle, the sun reaches solar maximum, a period of peak activity with the largest number of sunspots, solar flares, and coronal mass ejections, CMEs. During solar maximum, the alluring field becomes increasingly convoluted and tangled due to the continuous twisting and shearing from differential rotation and convection. As solar maximum fades, the alluring field begins to reconfigure itself. The reshaped and tangled magnetic field lines reconnect, and the global magnetic field gradually reverses its polarity. After the pole inversion, the sun enters a period of declining activity, returning to solar minimum. Eventually, the magnetic field reconfigures again, and the cycle begins anew. Currently, we are in the solar maximum stage, and the sun's magnetic field is about to flip. During this stage, we can expect to see some activity from the sun that could be as hazardous as it is captivating. However, the sun's magnetic field inversion is not an abrupt flip. Rather, it is a gradual process. Scientists monitor the sun's magnetic activity using various instruments and techniques. Observatories equipped with powerful telescopes, both on Earth and in space, provide detailed images of the sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, measure the sun's magnetic field and its changes over time. One key indicator of an impending magnetic inversion is the behavior of sunspots. During solar maximum, sunspots appear more frequently and become more pronounced as they migrate toward the sun's equator, signaling that the magnetic field is becoming more unstable and preparing to flip. Sunspots themselves are fascinating solar features. When the sun's magnetic field lines become wound and tangled due to differential rotation, they suppress the convective movement of hot plasma from the sun's interior. This results in cooler, darker patches that we see in sunspot images. Sunspots can sometimes produce powerful solar flares and coronal mass ejections, CMEs. These phenomena release enormous amounts of energy and charged particles into space. When directed toward Earth, they can disrupt satellite communications, affect power systems, and pose risks to astronauts in space. Additionally, increased solar activity can enhance auroras, raising radiation levels in Earth's upper atmosphere. While solar flares and CMEs are related, they are fundamentally different. Solar flares are sudden, intense bursts of radiation caused by the release of magnetic energy associated with sunspots. They emit large amounts of energy and light, such as X-rays and ultraviolet radiation. In contrast, CMEs are massive releases of solar wind and magnetic fields from the solar corona. They can be seen as giant bubbles of gas and magnetic fields being ejected into space. CMEs can cause geomagnetic storms that disrupt power systems, satellite operations, and navigation systems. They also enhance auroras but pose significant risks to Earth's technology and infrastructure. While the sun's magnetic field inversion does not directly affect Earth's climate, the associated changes in solar activity can have some influence. For example, increased solar activity can lead to slight warming of Earth's atmosphere, potentially fueling existing climate change. On a positive note, one of the most striking effects of increased solar activity is the enhancement of auroras, providing a mesmerizing display in the night sky. Auroras, also known as the northern and southern lights, occur when charged particles from the sun interact with Earth's magnetic field and atmosphere. These particles, carried by the solar wind, collide with molecules in Earth's upper atmosphere, causing them to emit light. The result is a stunning display of colorful lights dancing across the sky, predominantly near the poles. During periods of heightened solar activity, such as solar maximum, auroras can be seen at lower latitudes than usual, making them accessible to more people. While these displays are breathtaking, they serve as a reminder of the immense power of the sun and its potential to affect our planet. However, the risks associated with solar activity cannot be ignored. Geomagnetic storms caused by coronal mass ejections, CMEs, can disrupt modern technology. For example, in 1989, a powerful geomagnetic storm caused a widespread blackout in Quebec, Canada, affecting millions of people. Such storms can damage power grids, interfere with GPS and communication systems, and even pose risks to airlines flying at high altitudes. In addition to technological impacts, space exploration faces unique challenges during periods of intense solar activity. Astronauts on missions outside Earth's protective magnetic field, such as those traveling to the Moon or Mars, are particularly vulnerable to radiation from solar flares and CMEs. Spacecraft must be designed to withstand these events, and mission planners must carefully monitor solar activity to ensure crew safety. Despite these risks, scientists continue to study the sun to better understand its behavior and predict solar activity. Advanced models and satellite-based observatories provide invaluable data, helping us mitigate the impacts of solar events. For instance, agencies like NASA and NOAA issue space weather forecasts to inform industries and governments about potential solar threats. Looking to the future, as our dependence on technology grows, the importance of understanding and preparing for solar activity becomes even more critical. Efforts to create more resilient infrastructure, such as hardening power grids and improving satellite shielding, are essential to reducing the risks posed by the sun's ever-changing magnetic field. Finally, the sun's magnetic field reversal. While a natural and recurring phenomenon, serves as a reminder of the interconnectedness between our star and our planet. From the dazzling beauty of auroras to the potential for disruption to our modern way of life, the sun's influence is vast and multifaceted. As scientists continue to unravel the mysteries of the solar cycle, we gain not only a deeper appreciation for our star, but also the tools to better coexist with its dynamic nature. Striking lights, these normal light shows, known as the northern and southern lights, happen when charged particles from the sun interact with Earth's magnetic field and atmosphere. We frequently hear about the aurora borealis. However, these lights can also be seen around the South Pole. During periods of high solar activity, auroras become more frequent and can be visible at lower latitudes, offering dramatic night shows. However, aside from the beautiful auroras, there are also more concerning aspects of the sun's magnetic reversal that could occur if we are unprepared. One of the primary dangers associated with a magnetic field reversal is the increased likelihood of geomagnetic storms. These storms happen when the solar wind, overloaded with charged particles, interacts with Earth's magnetic field. In extreme cases, they can cause widespread power outages and damage communication systems. One such event occurred on the morning of September 1st, 1859. Astronomer Richard Carrington was observing the sun through his telescope, as he had done many times before. However, what he saw on this particular day would go down in history as the first recorded solar storm. At 11:18 a.m., Carrington observed a brilliant flare of white light emanating from a group of sunspots. This event, now known as the Carrington event, marked the beginning of the largest geomagnetic storm ever recorded. The white light Carrington saw was a massive solar flare, a powerful eruption of radiation caused by the release of magnetic energy stored in the sun's atmosphere. This flare was so intense that it triggered a massive coronal mass ejection, CME, directed toward Earth. The CME reached Earth in just 17.6 hours, an unusually short time, considering the sun is 93 million miles away. When the CME hit Earth's magnetosphere, it triggered an exceptionally strong geomagnetic storm. The impact was swift and widespread, disrupting Earth's magnetic field and inducing currents in the ground. Furthermore, transmission lines, used as the backbone of global communication at the time, suffered severe interruptions. Sparks flew from telegraph machines, operators were shocked, and some telegraph stations even caught fire. The induced currents were so strong that operators could send and receive messages even after disconnecting their batteries. One of the most striking and visible effects of the Carrington event was the brilliant display of auroras. The auroras were so bright and widespread that they were visible far beyond the usual polar regions. People as far south as the Caribbean, Mexico, and Hawaii reported seeing the sky illuminated with vibrant colors. The auroras were so extraordinary that they lit up the night sky, allowing people in the northeastern U.S. to read newspapers by their light. In the Rocky Mountains, gold miners reportedly mistook the brightness for sunrise and began preparing breakfast. The sky was described as glowing with red, green, and purple hues, shimmering and dancing across the horizon. Now, imagine if a solar storm of the magnitude of the Carrington event were to hit Earth today. The consequences would be devastating. The sun is currently undergoing a significant change, the reversal of its magnetic field, a process that occurs roughly every 11 years as part of the solar cycle. This event, driven by the solar dynamo, could have far-reaching repercussions for Earth, potentially causing disruption and disaster. The sun's magnetic field is created by the movement of electrically charged gases in its interior, generating a complex magnetic field that eventually reverses its polarity. The sun is primarily composed of hydrogen and helium plasma, with energy generated by nuclear fusion in its core. This energy is transferred outward through the radiative zone and then by convection in the outer layers. The solar dynamo, operating in the convective zone, produces the sun's magnetic field. The differential rotation of the sun, where the equator rotates faster than the poles, stretches and amplifies the magnetic field lines, driving the solar cycle. Currently, the sun is in the solar maximum phase, where sunspots and solar activity are at their peak. This peak activity can lead to solar flares and CMEs that disrupt satellite communications, power systems, and pose risks to astronauts. Scientists monitor the sun's magnetic activity and sunspot behavior to predict when magnetic field reversals will occur. Sunspots, resulting from tangled magnetic lines, can release solar flares and CMEs, both massive releases of energy that affect Earth in various ways. While solar flares emit radiation, CMEs release vast amounts of solar particles into space. These phenomena can enhance auroras, but also pose significant risks to Earth's technology and infrastructure. The sun's behavior is a fascinating interplay of physics and natural phenomena, impacting not just our solar system, but also life on Earth. Understanding the intricacies of solar activity is crucial, especially as we continue to rely on technology that can be affected by solar events. The sun generates energy through nuclear fusion, converting hydrogen into helium and releasing vast amounts of energy in the process. This energy passes through the sun's layers, eventually reaching the surface and radiating into space. Solar activity can manifest in many forms, including sunspots, solar flares, and CMEs. Sunspots are cooler regions on the sun's surface caused by magnetic activity, appearing as dark spots. These variations in solar activity follow an approximately 11-year cycle known as the solar cycle, with periods of high activity, solar maximum, followed by quieter periods, solar minimum. During solar maximum, the number of sunspots increases, leading to more frequent solar flares and CMEs. Solar flares are sudden bursts of energy that emit radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. These intense bursts can disrupt radio communications and pose risks to astronauts in space. CMEs, on the other hand, are massive releases of solar wind and magnetic fields that erupt from the solar corona and are propelled into space. When directed toward Earth, these ejections can cause geomagnetic storms that disrupt the planet's magnetic field, creating stunning auroras but also potentially causing technological disruptions. The effects of solar activity extend beyond space. They influence Earth's atmosphere and surface. Studies suggest that variations in solar radiation can affect climate patterns, potentially contributing to weather phenomena. Increased solar activity can also lead to atmospheric warming, a significant factor in discussions about climate change. In addition, the potential for technological disruption due to solar storms cannot be underestimated. A severe geomagnetic storm could damage electrical systems, disrupt satellite operations, and affect navigation systems. Preparing for such events involves monitoring solar activity and developing strategies to mitigate their impact on infrastructure. Scientists continue to study the sun's magnetic field and its cycles to better predict when significant solar events may occur. This research combines ground-based and space-based observatories that track sunspots, measure magnetic fields, and study solar wind. With advancing technology, our ability to predict solar activity is improving, which is crucial for protecting our technological infrastructure and ensuring the safety of astronauts as we explore space. As we study the sun, its impact on Earth becomes increasingly evident. The understanding of the sun's impact extends to its role in shaping the solar system. As the central star, the sun exerts a gravitational force that governs the orbits of planets, asteroids, and comets. This force has been instrumental in the formation and stability of our solar system over billions of years. However, the sun is not a static entity. Its life cycle spans billions of years, transitioning through stages that will eventually lead to its demise. Currently, the sun is a main sequence star, steadily burning hydrogen into helium in its core. This phase, which has lasted approximately 4.6 billion years, is expected to continue for another 5 billion years. As the sun exhausts its hydrogen fuel, it will enter the red giant phase, expanding dramatically and engulfing the inner planets, possibly including Earth. During this stage, the sun's outer layers will be ejected, forming a planetary nebula, while its core contracts into a white dwarf, a dense, dim remnant that will gradually cool over time. The eventual fate of the sun, serves as a reminder of the dynamic and finite nature of stars. While this transformation lies billions of years in the future, understanding stellar evolution helps scientists predict the life cycles of other stars and the potential habitability of exoplanets in distant systems. Back on Earth, the sun's influence is felt in subtler, yet profound ways. Solar radiation drives the planet's weather systems, powering the water cycle and supporting life through photosynthesis. Variations in solar output, though small, can have measurable effects on global temperatures and climate patterns. For instance, the Maunder Minimum, a period of low solar activity from 1645 to 1715, coincided with the Little Ice Age, a time of cooler temperatures in Europe and North America. While solar activity is not the sole driver of climate, its role in conjunction with other factors highlights the interconnectedness of Earth systems. Modern technology allows scientists to study the sun with unprecedented precision. Spacecraft like NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter have ventured closer to the sun than ever before, gathering data on its magnetic fields, solar wind, and corona. These missions aim to unravel long-standing mysteries, such as the mechanisms behind the sun's superheated corona and the origins of the solar wind. On Earth, ground-based observatories equipped with advanced instruments provide complementary insights, enabling researchers to monitor solar activity and predict space weather events. This knowledge is vital for safeguarding satellites, power grids, and communication networks from the disruptive effects of solar storms. As humanity ventures deeper into space, understanding the sun becomes even more critical. Astronauts on long-duration missions to the Moon, Mars, or beyond will face increased exposure to solar radiation, necessitating robust shielding and early warning systems. The success of these missions depends on our ability to anticipate and mitigate the sun's impact. In addition to its challenges, the sun continues to inspire awe and wonder. Its rising and setting define the rhythms of life on Earth, while its light fuels the growth of plants and provides energy for countless ecosystems. Culturally, the sun has been revered as a symbol of vitality and renewal, shaping myths, traditions, and art across civilizations. Looking ahead, our growing understanding of the sun opens new possibilities for harnessing its energy. Solar power, a clean and renewable resource, holds the potential to address global energy needs while reducing dependence on fossil fuels. Innovations in solar technology, from more efficient photovoltaic cells to large-scale solar farms, exemplify humanity's ability to adapt and thrive using the resources provided by our star. In many ways, the story of the sun is the story of life itself. From the earliest moments of Earth's formation to the emergence of complex organisms and the rise of civilizations, the sun has been a constant presence, shaping the conditions for existence. As we continue to explore its mysteries, the sun reminds us of our place in the cosmos and the delicate balance that sustains life on our planet.